You'll want to start off by copying down some notes. Pause the video if you need to. Also, as problems come up, I'll show you a copy of the problem, pause the video to write it down, then work it out with us. So we've looked at a bunch of different ways to analyze solutions. For a quick little review, go ahead and write this down with me. We know that if we compare these two solutions together, if I compare these two solutions together with the dots being solute, dissolved, in solvent, what's a vocab word to describe this one? Concentrated, perfect. That was faster than the other two classes, I'm impressed. All right, concentrated. All right, so if this one's concentrated, then we can automatically assume that that one is more dilute. Beautiful. All right. And you can't really make this next jump without looking at a curve, but you could say that this one is more saturated than that one, right? This one would be more towards maybe the saturated, supersaturated, maybe, but this one would certainly probably be unsaturated, simply meaning that if you added more solute, it would be able to dissolve it. We're going to take this one step further, which will be to actually count the dots. To actually say, well, how much have you added in there? Because what you'll see is that the strength of the solution is going to be based on how much solute is dissolved in it. And one of the properties that we're going to use to label that is what's called molarity. For example, I could label this beaker 18 molar and this beaker 2 molar, and I want you to understand conceptually what that's referring to. Molarity, as you copied down at the beginning of class, is represented by a capital M. When it's used as a unit, we call it molar. So this is 18 molar, referring to its molarity, its strength, 2 molar, a weaker, more dilute solution. Now, what's cool about this in regards to what I do in that room next to you is most of the stock solutions that I get from the company, the stuff that they won't let you order without a proper license, comes as 18 molar. And that's the real super burn through your desk dangerous stuff if I'm referring to it being an acid. I'm not legally allowed to let you be in the same room with that stuff. So the 18 molar stuff, to prepare it for a lab, I need to make it become 2 molar. I can make this solution become that solution. What do you think I do to make the strength go way down? Add more solvent, and what solvent is probably the most common one? I just dump water. And as soon as you start dumping water into a solution, the molarity starts to drop. Now, there's another equation to use to find out exactly how much water to make 18 molar become 2 molar, and we're not looking at that today. But yeah, to dilute it, I just add more water, and the molarity drops. But really, in terms of molarity goes, that means that the concentration of the particles, they get to spread out, so it dilutes it, and it makes the solution weaker by diluting it. Molarity looks at the liters. If you look at those two equations over there, you'll notice that the blue one for molarity looks at the amount of liters of solvent, whereas molality, the other one, very similar. These two equations have a lot in common. But the difference is that molality looks at the mass of the solvent. So both of them are putting moles of solute in. All right, we're dumping in solute. But the way that we do those solvents, I won't give it back. All the way away. I won't give it back next time. The way that the solvents are compared to each other is one of them looks at how much solvent you have, volume, while the other one looks at the mass of the solvent, kilograms. I do want to point out that both of these are colligative, and when I say colligative properties, we know that those are properties that it doesn't matter how much is being added, it changes the property the same way. What that means is if you're dumping solute in, molarity goes up. You don't have to say, well, what are you dumping in there? It doesn't matter. If you're adding more solute, molarity's going up. And we've talked about, and same with molality. And we've talked about other colligative properties like freezing point. All right, if you add solute, the freezing point depresses, no matter what the solute is. That's what makes it colligative. Is you don't have to ask, well, what solute? Just by dissolving more particles makes freezing point go down, boiling point go up, and all these other natural occurrences that the solutions will behave by. But what I want us to be able to do, besides just look at this idea, okay, one's weaker than the other, is for me to give you a solution scenario, and you can analyze it based on any of these variables. This will be the first problem we're working. For where we are right now in chemistry, the molarity and the molality equations are not going to overlap each other, meaning that you're going to run into one type of problem or the other, not both. So look at this problem. Look at the wording. Is it a molarity or molality problem? How do you know it's molarity? Capital M. All right. So right away, if we said it's molarity, I'm going to write down the molarity equation. Molarity equals moles over liters. That's the equation that's going to solve this problem. And since we're about to do a lot of converting, here's another step I suggest you take. I'm going to break the equation up into its parts so that I can just slowly identify which ones I have and which ones I'm still looking for. All right, these are the variables that we're going to have to be identifying. So now I've got a quick way to see what I have and don't have. So this looks at a solution of NaCl, that's sodium chloride, salt water. Let's pull out the numbers and see what information it has provided us. All right. First, I see 0.3 liters. Hey, check it out. I got a spot for liters. 0.3 liters. The other value given is 4.5 molar. Hey, check it out. I've got a spot for that too. 4.5 molar. So I've used both of the numbers they've given me. And if I have two of them, I can always find the other. So let's go ahead and we can solve for moles. Let's find this value. All right. There's our equation. I've got a big M is 4.5. Moles is the only value that they have not given us. And I have a volume of 0.3. You can algebraically solve this a couple different ways. When I was your age, I always put a whole number over 1 and cross multiplied. I thought that was easiest, but whatever, get the right answer. If you cross multiply, you'll get x one way, and then you'll go 4.5 times 0.3 the other. Go ahead and find that. I get 1.4. 2 sigmas. Now, realize what we just found. We just found moles. 1.4. That was the only part of the equation that we had left, right? Look at the question. What are we trying to actually find? Grams. And guys, this makes sense. Usually in the lab setting, I don't send you to a beaker and say, hey, go get 20 moles of this. What do I usually ask you to find? Grams, because we can more quickly calculate that. So it makes sense that most of the problems will refer to grams because I try to make this as real life as possible. Now, this is not the answer to the question, but you've been trained a million times how to turn these moles into grams. I know that if I take these 1.4 moles that I just got, that I can make them become grams in a one-step conversion. I know that what's true about the diagonals, they're at the same unit, and I'm trying in this problem to get grams. Now your conversion factors are over there if you look in red. All right, it's the same ones it's been for months and months and months in here. But it's PT to 1. PT, this problem deals with NaCl. So I need the molar mass of Na, one of them, Cl, one of those. Find it for me. Don't sit there and watch your classmate type on the calculator. Find it. What's the molar mass of NaCl? 58.433, is that what you said? Of course, to solve, we'll multiply across the top and divide by the bottom. And that will get you your final answer of 82 grams. You won't get confused in these problems if you slowly connect the variables to information that you have and then expect a grams conversion somewhere. Not always. Not always. Like this problem could have asked for moles. If it would have asked for moles, that would have been your answer. Just read through the wording carefully and just make sure that your units match up. This will be the second problem that we work on. So it's obviously a molarity problem. It asks for molarity. So I'm going to go ahead and leave this equation up the way I have it written. You'll have to rewrite this part. You don't have the benefits of a whiteboard. But now we can take it again number by number and plug stuff in as we get it. Let's start with the first value, 151 grams. Now right away, I don't have anywhere to put that. And when I run into that problem, you can identify and analyze all the numbers at the beginning, but whenever I run into a number that I don't have anything I can do with it, I like to change it into something I need first. Which of these can I easily turn grams into? I can make him moles. So let's do that right away. Let's get rid of this number. And we know that we want the diagonal units to match. And we said, well, let's convert this to moles so that it's usable. Now again, your conversion factor is over there in the red. 1 mole equals periodic table grams. This time we're looking at PT of K3P. That's potassium phosphide. So again, help me out. 3 Ks, 1 P. Anybody have that molar mass? 0.268. We cool with that value? That's K3P. So multiply across the top and divide by the bottom, which is ultimately 151 divided by 148.268. And you're going to suddenly get a value that you can use, which is moles. And I get 1.02. There's a mole number. Now, all we did there was we analyzed one of the numbers it gave us. Let's look at the other number it gave us. 26 liters. Hey, there's a spot for that, right? 26. What is this question asking for? Molarity. So now we're good to go, right? These two numbers can give me that number. To find molarity, it's simply moles divided by liters. I get an answer of 0.0392 when you consider sig figs. Three sig figs, 3 sig figs, 3 sig figs. Starting zeros are never significant. Hey, what would happen if this solution that we just analyzed, if I pour some of it on my skin, how quickly do you think I'd try to run to the sink? Not very quickly, right? I probably wouldn't even realize that I spilt it on myself. How do I know that? Because look how weak the molarity is. The molarity is so small that you wouldn't really feel it. All right. Now, you don't have a real good basis for judging that. All right, but I'll tell you this, that double-digit molarities are all high. All right, even single-digit molarities above 4 are all considered pretty strong. Most of the stuff I give you is 1 molar and 2 molar. All right, but 0.03 molar, that's so dilute, there's a good word, so dilute, that it's not a very dangerous solution. Let's keep going. Problem 3. Molarity and molality are both colligative. That's what they have in common. The difference is this molality problem is in mass of solvent instead of liters of solvent. But we're going to analyze it the exact same way. Here's why you commonly think these are a tad more challenging. Look at the problem as a whole. Look at both of the numbers that it's given us. What units are they both in? They're both in grams. That's going to cause us to think an extra second on what's what. But in order to do that, I want you to look back over at the actual equation for molality. Not only does it say moles over kilograms, but more specifically, it's moles of solute over kilograms of solvent. And that's really going to help you out a lot. What's our most common solvent? Water. Water. And I help you use that to your advantage when I ask you molality problems. So let's take a look at these numbers. The first number it gives us is 120.4 grams. I look here and I see that grams goes nowhere. So I'm going to try to fix it right away. 120.4 grams. Here's the question though. Is this value describing the solute, which is on top, or the solvent, which is on bottom? How do you know it's the solute? Because the other guy is water. That's a real good way to go do it. All right? So this is my solute, and I know by looking at the equation that the solute is supposed to be in what units? Moles, because the solute is up top. So I don't want this to be grams. I want it to be moles, and this will fix it. Are there any questions on what I just did? That's what I said. When I'm asking you molality problems, I'm not going to make it questionable what's the solute or solvent. I know exactly how much chemistry you know. So I'm not going to throw you two things you never heard of and just smile vilely at you. All right? So we know the conversion factor here is 1 to PT. I need the PT of NBr2. Help me out. What's that molar mass? 173? Yes. 0.815? Yes. There he is, NBr2. Multiply across the top, divide by the bottom. 120.4 divided by 173.815. And I'm going to get a mole number. Now keep in mind what you're doing so you don't get lost in the maze here. I'm going to get a solute mole number of 0.6927. And I fixed one of the numbers that it started me out with. Hooray. Let's go to the other number it gave us, 376 grams. Uh-oh, grams does not go in either of the other two spots. So it must need to be something different. But you'll notice that this one is the water. This one is the solvent, which we know goes on bottom. We need it to be in kilograms. Now, there's a really easy way to make grams go to kilograms. It's called a decimal slide. I know some of y'all don't agree that it's easy, but if you slide the decimal to the left 3 times, it turns into kilograms. If you don't like that idea, you can use a grid to do it. I give you the conversion factors over there. We know that the diagonals will match. We don't want grams, we want kilograms. And the conversion factor says that 1 kilogram is 1,000 grams. So if you run that little mini grid, you'll still get the same answer here, 0.376. Any questions there? I'm all out of numbers to analyze. So now the question wants to know molality, and I'm ready to go. To find molality, it's moles divided by kilograms. So put that in and we'll be done. I get 1.84 molal. Here's our fourth problem. Our next problem is another molality problem because of the little m. So again, I want to take it number by number, put things where I can, fix them if they don't fit anywhere. All right. The very first number that I have is 7.00 grams, and grams goes nowhere in my molality equation. So I need to figure out, is this 7 grams of solute up top or 7 grams of solvent on bottom? Look closely, what is it? It's solute, all right, because the other one's referring to water, so I can safely assume that this one is not supposed to be in grams, it's supposed to be in moles because it's the solute. So we can change him to moles very easily. The same units diagonal, and we want moles. The conversion factor is in red on the other board. It's 1, and grams is periodic. This one's pretty easy for the PT because it's just krypton. So you can go and look up 1 Kr and get 83.798 and solve the grid. Now remember what we solved for. We found the moles, which is right here, and I get a value of 0.0835. Let's go to the next number that the problem. It appears that it's 0.5 mole. Hey, check it out. I got a spot for that number. He goes right here, right? Didn't have to do anything. And now we have everything we need to solve another missing square. If I've got 2 of them, I can solve for the third one. So let's plug and go. My mole is 0.5. My moles is 0.0835. My kilograms, the mass of the solvent, we're going to find that. We're all out of numbers, so we can find that number. And we'll cross multiply to solve. I'm going to get 0.5x over here. Divide by the number connected to the x. Well, there was nothing, so I cross-multiplied. When I cross-multiplied there, I got that. When I cross-multiplied there, I got that. And then I divided by the number connected to the x on both sides. Sorry, I didn't draw these zeros. But what kilogram count do you get? 0.167. Who can find the problem that we still have, though? What's the question one?
Grams of water.
What's grams? My equation can't spit out grams. It spit out kilograms, and we can convert. So, this is not the answer, but it certainly would be a choice. So you've really got to go through these carefully to make sure you have arrived at exactly what part of the solution is the solution. Get it? So I'm going to take my 0.167 kilograms and turn it into grams. Now again, you can just slide this decimal. This time to the right 3 times and you're done. Or, if you want to do a grid, kilograms will match. We're going to grams. And as the purple conversion factor over there says, there's 1,000 of those in one of those. But either way, you're going to get a final answer of 167 grams. Don't put your stuff away. We got one problem left. This will be our last problem. Pause and work out. I'm going to start to pull the numbers out. The first value that it gives me is 9.48 mole. Well, that's nice because that's one of the values that I know that I need. So there's that. Then it gives me 806 grams. Grams goes nowhere. So I need to do something with 806 grams. It's described as being water. So I'm going to assume that this is the solvent and needs to turn into kilograms. I can easily turn my grams into kilograms by doing a decimal slide 3 to the left. Or you could put grams down there, kilograms up there, and say that there's 1,000 of those in one of those. Either way, your kilogram will come out to 0.806. I can use these two numbers to find this number. My molarity is sitting there at 9.48. My moles is currently not known, and my kilograms is 0.806. All right? I like to cross multiply to say x equals. We go the other way, 9.48 times 0.806, and I get 7.64. Now, that is my mole count. If the problem was asking for moles, and sometimes it will, and you'd be done. It wants grams. So these moles are no good. But I'm able to easily turn them into grams. The diagonal matches. PT over 1. And this is the chemical found on frogs because we're looking for the mass of ribbit. What is the mass of RBAT?
295.468.
295.468 is 1 rubidium and 1 astatine. So by solving the grid, which is just going to be multiplying, if you look at sig figs, your final answer will be 2260.